4. Again, the problem is listed in the book at the end of chapter 2. Problem number 4, that's the bad news. The good news is do the first part only. Just the first part, the rest is not really important, but you do it if you want. But anyway, please do the first part. All right, that's that. Then we have, okay, where were we? So, where we were last time, so we now know how to do quantum field theory. You've got a classical field theory. So, for example, you have the real Klein-Gordon field. Obeying this wave equation, the Klein-Gordon equation, and you find a Lagrangian density, which gives you that equation. May as well write it down. I actually don't like writing it this way very much. I prefer to put, let's put G alpha beta, phi alpha phi beta. Whoops. Minus m squared phi squared. And from the Lagrangian density, we find the canonical momentum, or rather the canonical momentum density comes out to be phi dot, and then we find the Hamiltonian density, which is pi phi dot minus the Lagrangian density, and this implies the Hamiltonian, which is the integral over all space of the Hamiltonian density. So, all right, and for the case of the Klein-Gordon field, this comes out to be a half integral over all space of pi squared plus grad phi squared plus m squared phi squared. Okay, there are three terms here. Pi squared plus grad phi squared plus m squared phi squared. Integrate over all space. That is your Hamiltonian. Now that's just classical field theory. The quantum field theory you construct by promoting these phi and pi to operator fields that obey the canonical commutation relations. So we have phi hat xt pi hat x prime t equals I. I'll leave out the h bar. What is wrong with this chunk? Minus x prime, etc. Etc. meaning phi's commute with each other, pi's commute with each other. All right, so that's where we were, and of course, we now have a Hamiltonian operator which is equal to the integral over all space just the quantized version of this. So integrate over all space pi hat squared plus grad phi hat squared plus m squared phi hat squared. All right, so that's where we were. And so we promote the fields of operators, obeying canonical commutation relations. Everything over there now becomes an operator. Now we should get, if we've done this properly, we should get the Klein-Gordon equation for the operator field in the Heisenberg picture. We should get that. Well, where does that come from? This comes from the Heisenberg equation of motion. So the Heisenberg equation of motion says that any operator, the time derivative of any operator, is equal to minus I times the commutator of the operator with the Hamiltonian. So what you have to do is you have to apply this equation to the quantities phi and pi. So this is what you do in exercise 2.2. So in exercise 2.2, you should be able to derive this equation from the Heisenberg equation of motion. Now, just to make sure that you get this, I'm going to do a little bit, just have a little look at least the first part of exercise 2.2. And just to remind you, this is the same as, so if you're, just to make sure that you understand what's going on, you might want to just think about the analogy. Is it the damp that's making the chalk do this? Anyway, you might, it's not my day. You might want to think about the analogy with one particle, let's say one dimension. I've discussed this before, but let me just say it again. In the Heisenberg picture, this implies that dx, and you should check this, that dx by dt is momentum over mass. And it implies that dp by dt is equal to minus the gradient of v. Okay, in other words, it implies the Klein, so please check that. This, of course, using the commutation relation, right? I put h bar equal to 1. Okay, you should be able to work out the commutator. So this is just minus I, the commutator of x with h. So work out the commutator of x with h, multiplied by minus I. Okay, you should get p over m. That's dx dt. This here is just minus I times the commutator of p with h. So dx dt, x, h, so x commutes with this, x with p, and we're going to do dp dt, p. Anyway, so you should know that. You should be able, if you're not unsure of that, please go through it and make sure you understand that, because what's happening here is just the same thing. So in exercise 2.2, you're asked to show that the commutator let me write it this way the other way around. I've written it the other way around. Let me write it like this. The commutator or phi xt with h is equal to I phi hat xt. You're asked to show that. And to show that the commutator of phi hat with h is equal to minus I. Actually, let me write it this way around. So here they've got the commutator flipped around. I L squared minus m squared phi hat xt. Now, if you can show this, then you're home, because, well, phi hat dot. What is phi hat dot? The Heisenberg equation of motion tells you, well, that is minus I commutator of phi hat with h. And of course now, this is our Hamiltonian. All right, this is our Hamiltonian here. If phi hat h is the I pi, then minus I times I is 1, so we have pi hat. So we find that phi hat dot is just pi hat, which CF, the classical, remember classically, the canonical momentum density is just phi dot. So we find there's a consistency. The quantized operators obey the same relation. Pi hat is just phi hat dot. From this second commutator, if I now look at, let's look at phi hat 2 dots. Well, phi hat 2 dots, in other words, the second time derivative of the field operator phi, what is that? That's the time derivative of phi dot. In other words, it's the time derivative of pi, or pi hat, okay? What's the time derivative of pi hat? Well, from the Heisenberg equations of motion. Sorry, the Heisenberg equation of motion. Right, so phi 2 dots is just pi dot, which is minus I commutator of pi with h. So from this result, I have a minus I get del squared minus m squared phi hat. And so that is just the Klein-Gordon equation. So again, I find consistency that the operator field obeys the Klein-Gordon equation, just like the classical field. So exercise 2.2, you have to prove that these commutators have these values. And just to show you how nice I am, I'm just going to go through the first one a little bit, just to make sure that you know what you're doing and what you need to do, and do it properly. Okay, so let's just have a quick look. So I'm cheating a little bit because the first commutator is the easy one. I'll leave the hard one for you to sweat over. All right, so let's just check we know what we're talking about here. How do we find this commutator? We have to calculate the commutator of, so we have the field operator at a point x and a time t. We're taking the commutator with the Hamiltonian. All right, what is the Hamiltonian? The Hamiltonian is equal to this. But in order not to confuse, we don't want to get confused between our x for a particular point and x for an arbitrary point. So let's replace here the x by x prime. Okay, so here we can just put primes in the argument. So we'll write our Hamiltonian as a half integral with respect to x prime of pi hat squared evaluated at the point x primed and at time t. Okay, we go through this slowly, carefully, just to make sure we know exactly what we're doing. Here we've got the field operator at the point x primed and time t, its gradient, plus m squared phi hat squared at x prime and t, integrated over all space. Now, if you've not done this sort of thing before, you might start to panic. But remember, the integral is just the limit of a sum. Okay, if you start to worry, you can always just think, well, hang on, I could discretize this. I could imagine, just make a lattice of points in space. This is just a sum over points in space with the pi's and phi's evaluated at different points. And this gradient, what is it? The gradient is just the limit of the difference. I've got phi at this point minus phi at a neighboring point divided by some epsilon, some little distance. So that's all it is. This is just the sum of the pi squared at each point, the phi squared at each point, and a sum of squares of differences of phi's at neighboring points. So don't worry. There's nothing radically different here. So this is just a sum. Now you know that you can, if I've got a sum of a commutator with a sum of I take the commutator of something with a sum of terms, that's just the sum of the commutators. All right, so I can take this, I can take out, of course, the factor of a half. I can take out the integral, which is just a sum over the different points, and I can say, all right, what I need is I need the commutator, or I need this commutator. All right, so don't panic. Nobody's going to die. So phi hat x prime t squared plus m squared phi hat squared x prime t. All right, so I have to work out this commutator, and then of course the commutator here then is just, again, I can just break it down into a sum. So I have the following integral over x prime. Let me put a big curly bracket. I've got three commutators here. This is that phi hat xt commutator with pi hat squared x prime t plus the commutator of phi hat xt with the gradient of phi hat x prime t squared. All right, is that all right? Have I written that? Yes, right. Plus, let's write m squared commutator phi hat xt with phi hat squared x prime of t. All right, so here we have, so the commutator of phi with h that we're looking for is now an integral over three different commutators. So now we need to use our canonical commutation relations. So remember we have our canonical commutation relation, which we wrote down earlier. Now here I wrote etc. So there's this relation, and there is of course also phi hat. I take the commutator of the field at two different points at the same time, I get 0. And if I take the commutator of the momentum density operator at two different points at the same time, I get 0. All right, these are our canonical commutation relations. So let's look at this. Let's leave this one till last. It'll turn out this is the only one that's not 0. Let's maybe start with the easiest one. This one here. All right, now, once you've done this sort of thing a couple of times, it becomes obvious and you just write down the answer. But seeing as you've maybe not done this before, let's just go in baby steps and just check we really know what we're talking about. I mean, why this is obviously 0, because we're, the field operator commute, the field operator at different points. Field operators at different points commute. So the field operator here and the field operator squared at the other point obviously commute. Okay, but if you want to do it, formally, where you would say, okay, this is equal to this. Plus I've got if I've got an operator commutator with b squared is just ab plus b ab. So you should know this kind of thing. So I've just used that identity. So obviously, then each of this term is 0, this term is 0, this whole thing is 0. Okay, so that commutator is 0. Good. That's nice when something is 0. Good. Got it. All right, what about this one? Now this one, it might get you worrying. How on earth do I take the commutator of the field at this point with the gradient of the field at another point? Well, again, once you've seen this a couple of times, it will become obvious to you that this is also 0. But again, let's just do some baby steps. Seeing as it's the first time, let's write this as, all right, so the gradient squared, let me write this as, you write in terms of components. I phi hat x prime t di phi hat x prime t. Right, where I'm summing over i's. I've just written the gradient squared as product of first derivatives summed over, square of first derivatives summed over. I'm summing over I from 1 to 3. All right, so am I doing that right? I'm doing it right. All right, so again, just doing it baby steps. There we go. Let's write down phi hat x prime t and bring out this term plus di phi hat x prime t commutator of phi hat with di phi hat x prime t. All right, okay, so now you might be thinking, okay, how do I take commutator of phi with the derivative of phi? What am I going to do? Okay, so this is again obviously 0. Of course, it's obvious when you've seen it all before. Let me give you, I'm running out of blackboards. Okay, let me give you 2 ways to think about it. So here are 2 ways to think about it. One is that phi hat x of t. So if I think, what is this derivative? What is it really? It's really phi hat evaluated at x prime. Let me write. Okay, let me write plus a little vector epsilon I epsilon is a little displacement in the I direction. Okay, it's just this minus phi hat x prime t divided by the modulus of this little displacement. Okay, and obviously taking the limit. And what is the derivative? The derivative is just you take the difference to nearby points divided by the distance, take the limit. That's what the derivative is. So if you think about this, well, okay, so this is just 1 over epsilon I times what? I've got the commutator of the field at x with the field at x prime plus epsilon I minus the commutator of the field with the field at x, with the field at x with the field at x prime. Okay, so I'm just saying that the, whoops, there's another big commutator. So I'm just saying something trivial, okay? This is not what you would normally do. I hope in the exam you're not going to sit there. This is obviously 0. It's just because you've not seen it before. Well, okay, so look, phi of x commutated with phi of x prime times that is 0. Each of these terms is 0. This is obviously 0, okay? Let me give you a second slicker way of seeing the same result if you want to. In fact, let me just give you what is really the slick and clear way of proving the result. Let's call it way of seeing number 2 is let us first write down this commutator. We've got the commutator for phi x of t and phi x prime of t. All right, this is just one of our canonical commutation relations. The commutator of phi x with phi x prime is 0. All right, let us now take the derivative of this with respect to xi. With respect to so this di, there should have really been a prime here because these were derivatives with respect to x prime. Okay, all of these di's, there should be a prime, and sort of obvious implicit, but anyway, these are derivatives with respect to x prime. Let us take the derivative with respect to the ith component of x prime. Okay, so I can say, okay, so the derivative of this commutator must be 0, all right? And if I now write out the commutator, phi times phi of x prime minus phi of x prime plus phi of x, and I take the derivative with respect to x prime, well, these terms depend only on x. There are only these terms that depend on x prime, and so this implies that phi hat xt di prime phi hat x prime of t is 0. Okay, I hope that's clear. So I can just write out, this, as again I'm running out of space, but anyway, if you wanted to write out that commutator, you just write it out here. It looks like this. And if I take the derivative with respect to x prime, this is independent of x, so here I get the di primed. Here I get a di primed. And sorry, it's all squashed. But anyway, this is commutator of phi hat with the derivative of phi at the prime point. All right, so again, that's something that, once you've a bit of experience of this stuff, you just see, oh, okay, so I've got this commutator is 0, so obviously if I take the derivative with respect to x primed, I get that this is true. So the commutator of phi of x with the gradient of phi of x primed is 0. So, so what does that imply? So this is 0. So this here is 0. This here is 0. And so the commutator of phi hat with the gradient of phi squared is 0. All right, is it all going to be 0? It had better not be. So let's have a look finally at the first term there. So, okay, so let's look at, we want to evaluate the commutator of phi, the field operator phi at the point x, with the square of the canonical momentum density operator at the point x prime, with everything evaluated at the same time t. So this is again just pi hat x prime t, pi hat x t, pi hat x prime of t, plus t. So now something had better happen, something more interesting. So here we go. Finally, we have commutators that are not 0. The commutator of phi with pi is equal to I times the 3-dimensional Dirac delta function. So what do I have? Phi with pi, phi with pi. The Dirac delta function is a number, or really there's a unit operator. Remember, when you write down something like this, it's understood that there's a unit operator here, but which you don't normally bother to write in. But anyway, so what is this? This is equal, there are two terms, so I'll get 2i Dirac delta function times pi hat x prime t. So what do we have? Let's maybe, seeing as these terms are 0, so I used to have an evaluator who used to come to my class, always telling me, you shouldn't do this. You shouldn't rub out things like that. You've got to write out the whole equation again, because it confuses the students. But you are sharper than that. You understand what I'm doing. There you go. Look at that. I saved chalk. So, what do we do here? This is now, so remember we were working out the commutator of phi hat with the Hamiltonian. So it reduces to this one term. I have an integral with respect to half times the integral with respect to x prime of this commutator of phi with pi squared, which you've just worked out, is equal to 2i times the delta function of x minus x prime times pi hat x prime t. All right, I've just inserted this result here for that commutator. So now the final step. Here I've got, remember, pi hat is a field operator. It's a function of position. I'm integrating the operator times the delta function over space. The delta function just picks out the value where x prime is equal to x. I cancel out the 2's. So what do I get? I get I times pi hat at xt. And that should be, there we go, the advertised result. All right, ta-da! Hooray! So there we go. So we verified that commutator, and then the other one, which is more tricky to do, I'll leave to you to do that, exercise 2.2. So it's very important you understand this, so you see the mechanics of how the theory works. Once I've got my quantized operators obeying canonical commutation relations, once I have the Hamiltonian, I can then work out anything. I want the time derivative of any observable. I use the Heisenberg equation of motion, and I can work it out. And as I said, it should be consistent with the original classical field equations which he quantized in the first place. So, are there any questions about this? Okay. So you must, this should be this sort of thing we're going to be doing a lot of, and it's very important you have it straight. So, all right then. So let's move on, and I think someone during the night crept into my office and broke all my chalk. It's that demon again. There we go. So, all right. So we're going to move on and discuss the conservation laws in quantum field theory. So, last week you will have done conservation laws in classical field theory using Lagrangians and Noether's theorem. So we're going to look at those results in the quantum field theory. So, so let's see, so important thing. The Lagrangian density is invariant under a continuous transformation. So in other words, it has a symmetry, has a continuous symmetry. When I say continuous, it means there's some parameter, some continuous parameter. It could be a displacement. I can displace my system or the coordinate system by a small amount or larger amount, rotations, phase transformations. L is invariant under a continuous transformation. Then it implies there is a conserved quantity. A conserved quantity. And this is Noether's theorem. Noether's theorem. Noether's theorem. Something, okay, so for example, you will have seen this invariance on the time translation implies energy conservation. Invariance on the spatial translation implies momentum conservation. Invariance on the rotations implies, perhaps you didn't get right. Did you do angular momentum? I don't think you did, right? Okay, we'll have a quick look at that. So invariance on the rotations implies angular momentum conservation. And invariance under phase transformations which you did do, right? Remember, for a complex field implies charge conservation. Now, just something I'd like to get clear, because again, books don't really explain this very well. It can be a source of confusion. You might get the impression that this theorem is telling you something extra, but really it's not telling you anything extra. And here's what I mean. Let's say you have, just going back to very basics, let's say I have Newton's law. let's say I have Newton. Let me just do it in one dimension. Let me just do it in one dimension. Keep it simple. Let's say I have Newton's law in one dimension for particle moving in external potential V. Sorry, d squared Newton's law. This equation, if you integrate this equation, you can show that this equation implies that the half mx dot squared plus V is a constant. Okay, that's an elementary thing that you did way back in mechanics. If you integrate that equation, the first integral of that equation tells you that the kinetic plus potential energy is 0. Now what you can do is I can look in the, if I looked, I don't know if you would have done this, you could, if I look at the Lagrangian for this system, you can take the view that time translational invariance implies this thing here. You can say this is a consequence of time translational invariance. But you can just get it from the equation of motion. You don't have, there's nothing extra. You already know this from the equation of motion. Similarly, if you want a field theoretical example, let's say you write down Maxwell's equations in empty space. I always get the sign wrong. And I got that one right? I got that one. Okay. Yeah. Maxwell's equations in empty space. It is a consequence of these equations that if I take the integral over all space of E squared plus B squared, and let's say put in a factor of a half, and take the time derivative of the whole thing, then that is 0. And you can work that out. If you bring in the time derivative under the integral sign, it becomes a partial derivative with respect to t. If I replace E dot by grad B and B dot by by curl of B, and B dot by minus the curl of E, and I fiddle around with the integral, integrate by parts for some identity, something. Anyway, you get 0. This is a consequence of Maxwell's equations, that the energy, what we normally interpret as the total energy of the field, is conserved. Now what you can do is you can write down the Lagrangian density for the electromagnetic field. And we'll look at this later, which actually I think comes out to be a half E squared minus B squared, if I remember rightly. Anyway, the Lagrangian density to the electromagnetic field. And I can derive Maxwell's equations from the Euler-Lagrange equations. And then what I can do is Noether's theorem tells us that, well, T invariant, let me just for short, time translation and invariance, if you look at what's, Noether's theorem, because the Lagrangian density is time translation invariant, Noether's theorem tells you that the total energy is conserved. In other words, it tells you this. But you already know this, or you could have got it from Maxwell's equation. Okay, so I want to make clear to you, Noether's theorem doesn't tell you anything that isn't already there in the equation of motion. Okay? You say, well, then why do we bother with Noether's theorem? The reason is this, is that if you're given these equations, it's not immediately obvious that this is true. Whereas Noether's theorem, well, if I have a Lagrangian density and you see it's a time translation invariant system, you already know, well, there must be a conserved quantity associated with that, and there's a general expression for it. You can work out that general expression, comes out to be this. Whereas, if you're just given Maxwell's equations, well, it might not occur to you. You might play around with these equations for years, and it might never occur to you that, hey, there's this thing, that if I work out this integral, this is conserved. You know, you need some. So this is really what the power of Noether's theorem is. It gives you a way of immediately seeing what conserved quantities there are. But bear in mind that physically those conserved quantities are consequences of the equations. Okay? So if you want to check, those of you who are skeptical, you don't believe me, does he really know what he's talking about? There you go. Here's a little homework problem for you. Let's check. Let's take the Klein-Gordon equation. Let's take the Klein-Gordon equation. And we've said that the time translational invariance implies energy conservation, which means, so here we're just doing classical field theory. What does energy conservation mean? It means that the time derivative of the Hamiltonian is 0. What is the Hamiltonian? The Lagrangian formalism tells you that the Hamiltonian is equal to this, phi dot integral over phi dot squared plus grad phi squared plus m squared phi squared. All right. So the way it would have been presented to you is that, well, you can get this from Noether's theorem from the Lagrangian density. I write down the Lagrangian density. It gives you the Klein-Gordon equation. I see its time translation variant. So there's a conservation law. The conserved quantity, there's an expression for it, which you will have done. You work out that expression, it comes out to be this. Maybe check, this follows from this here. I don't need Noether's theorem. Okay? If you work out the time derivative of this, bring the time derivative under the integral sign, it becomes a partial derivative. I work out, I'm going to get a 2 phi dot, phi double dot. Use the Klein-Gordon equation, right? Phi double dot is del squared phi minus m squared phi. Substitute in here, fiddle around, probably some integration by parts. It'll come out to be 0. Okay? So you don't really need Noether's theorem. Of course, again, as I said, if you were just given the Klein-Gordon equation, it's not obvious that this quantity is conserved. So the power of Noether's theorem enables you to just write down what the conserved quantities are. But as I said, physically, it all follows from the equations of motion. So it's something, again, which for some reason tends not to be explained in books. So thank heaven you have me here to tell you the truth. All right, so let's now do a bit of get started on the conservation laws in the quantum field theory. So let's see. All right. So conservation laws. In quantum field theory. All right, so remember the Heisenberg equation of motion for any operator observable omega. The omega by dt is minus I omega, the commutator of omega with h. So, omega, so simple, so obviously, omega is conserved other words, d omega by dt is 0, or another way of putting it, omega is a constant of motion. Okay, just as he used to say, you know, for a particle, the kinetic plus potential energy is a constant of motion. As the particle moves, that quantity remains a constant. Omega is conserved, or is a constant of motion, if and only if the commutator of omega with h is 0. All right, simple, clear consequence of the Heisenberg equation of motion. If the commutator of a quantity with h is 0, then that quantity is conserved in time, it's constant in time. Something else to note about symmetries in quantum mechanics. You're used to thinking about the system, maybe different frames of reference. For instance, you transform from one Lorentz frame to another, you transform the electric and magnetic field using the Lorentz transformation, you've done these kinds of things. In quantum mechanics, symmetries in quantum mechanics, when I say quantum mechanics, remember quantum field theory is just quantum mechanics applied to a field. So in quantum mechanics, let's say I have, so for example, two frames of reference. Maybe I've rotated or translated or boosted the reference frame. So I have two equivalent descriptions. Of the same physics. Now in quantum mechanics, so what that means is I have my first description. What do I have? I have a quantum state psi, and I have operators omega. And in the Heisenberg picture, which is what we're using, psi is fixed and omega evolves with time, but actually that's irrelevant. It could be in the Schrödinger picture. Anyway, you've got at some given time, there is, well, we might be considering time translation. Let's say we've got a given system. There is a quantum state, there are operator observables. That's one description. My other description, maybe in this rotated frame of reference or whatever the transformation happens to be, is, well, I have a different quantum state. Let's call it psi prime. It's related to the first state by unitary transformation. And I have a different operator, omega prime, which is given by, so we have u hat omega u hat dagger. U hat omega prime, where, so u hat is a unitary operator. Unitary, so these are, so in other words, the two descriptions, the two equivalent descriptions are related by a unitary transformation. Maybe I can just put here, this can maybe look a bit too abstract, e.g. spatial translation. going to be u is going to be e to the I, let's call it e hat dot d. If d is, so say we have a spatial translation by d. Let's say I have, don't worry about this too much, but just give you a quick simple example. Let's say I've got a coordinate system, and let's say I displace the coordinate system a bit by some displacement d. Then this unitary operator is going to be e to the I p dot d, where p is the momentum operator. P is the momentum operator. I'll talk a bit about, I'll give you another example of that later. So because the momentum operator is observable, P is Hermitian, and so u hat e to the I, am I doing this right? E to the I p dot d is unitary. Now, just as an example, so what I want to say is that the unitary operator that appears here, of course, depends on what symmetry you're talking about. It's a spatial translation, and this is the unitary operator. Why is this, hang on, why is this equivalent description of the same physics? Why is it equivalent? So, first of all, so matrix elements are the same. So if I look at, for instance, let's say I work out say I've got one state and let's say I'm working out the matrix element. I've got an observable and I work out the matrix element where psi1, psi2 are two different states. And let's say I now work it out in the other description. So in other words, I have the prime state, I have the prime operator, I have the prime states. So what is this? Well, this is equal to psi1 prime. Here, this is going to be psi1 u hat dagger. Okay, I've taken the adjoint of this equation. So psi prime, just to make sure we know what we're talking about, this implies that psi prime is equal to psi u hat dagger. Alright, you should know that already. If not, go back and revise your Hilbert space quantum mechanics. Okay, what is omega prime? Well, we've defined omega prime to be u hat omega u hat dagger, and then psi prime, psi 2 prime is just by definition u hat psi 2. And what is this? Remember, u dagger u is 1, u dagger u is 1, so this is just psi 1 omega hat psi 2. All right, so clearly under this transformation, these two equivalent descriptions, these two descriptions are equivalent in this sense that, well, the matrix elements that you calculate are the same. The other thing is that the let's see, what else do I want to say? That the operator equations are the same. So commutators, field equations are the same. How do we see that? So let me, okay, I'm going to have to rub out some things here. Let's just have a quick look at that. Let's say I have a commutation relation. For instance, we've got our beautiful, sexy, canonical commutation relation. All right, what we can do here is let's say, look, let's multiply from the left by u hat and from the right by u hat dagger. All right, let's take this equation. So in other words, let's write down this here. Now this is just a number, and u hat dagger is 1. So I have this here. And then if I write out the commutation relation, if I write out the commutator, and then what I can do is I can insert, I better just make more room here. If only we had a third blackboard. I can now insert a u dagger u. I can put u hat dagger u hat. U dagger u is just 1. And I can do the same here. And now, well, what is this? This is just, remember our definition, we say that omega for any observable in the new description, the new operator is just u omega u dagger. So what is this? This is just my new field at the point xt. Okay, it's just the field in the new description. This is just the canonical momentum density operator in the new description at the point x primed. And similarly here, in other words, what I have is, I have this commutation relation. This is just the canonical commutation relation for the new field and for the new operators. So the canonical commutation relation stays the same under these transformations. Similarly, if I have a field equation, you can do the same trick. Let us say I have the Klein-Gordon equation. If I again do the same trick, let's say I multiply, let me make a bit of room here, this is equal to 0. Let us take this and multiply from the left by u and from the right by u dagger. Okay, this will imply that my new field operator obeys the same equation. So, generally, you might think, well, is that only because I had a phi? What if I had a phi hat cubed? What if I have a phi hat cubed? Well, remember, u hat, let's say you had a phi hat cubed instead of phi hat. U hat phi hat cubed u dagger is just u hat phi hat phi hat, u hat dagger, which is just u hat, phi hat. Let's put in a dagger, u dagger u, u dagger u. And you'll see that each of these terms is just, this is just my new field phi prime cubed. And similarly for any function. So this is, okay, so the operator equations are the same. The canonical commutation relations are the same when I perform this transformation to a new. So this is basically a general way of symmetry in quantum mechanics. I have two equivalent descriptions of the same physics. Now, there's an important result. Let me just give you this in 5 minutes, and then we've done enough for today. Let's see. Okay. Sorry, any questions about this, by the way? Any questions about that? Two different equivalent descriptions.
It is only the canonical commutation relationships which are invariant of the transformation. A general commutator will differ.
No, because again, you can do, if I have, let's say I have A hat, B hat equals C hat. And again, if you multiply, both sides from the left by u, and from the right by u dagger, then you get that A hat prime, B hat prime is equal to C hat prime. It's the same. Really, any operator equation, it will transform. So, okay. So now there's an important thing, connecting back to, remember this point we said that omega is conserved if it commutes with the Hamiltonian. So now there's a very nice point here that comes up a lot, is that we can write, remember here u hat is unitary. Alright, this is a unitary operator. Now I can always write a unitary operator as an exponential of I times a Hermitian operator, because I'm having I want a continuous, let's include a continuous parameter alpha. So T hat is Hermitian. Alright, that's just a general. I can always write unitary operator, e to the I times a Hermitian operator, and let's take alpha to be a continuous parameter. Now, what we can do is, it's a continuous real parameter. Of course, alpha has to be real in order for our u to be unitary. All right, so we've just rewritten u in terms of t, where t is Hermitian. So now let's look at very small alpha. So we're looking at what sometimes people like to call an infinitesimal transformation. For very small alpha, u hat is equal to, or approximately equal to, 1 plus I, let's write delta alpha, t hat. Infinite, very small alpha, so let's call it delta alpha. Okay, this is something not a very clever notation. But anyway, very small alpha, we're going to call it delta alpha. So 1 plus I delta alpha times t. That is our unitary transformation. So now, let's look at what happens to this here, omega prime, which is u hat omega, u hat dagger. What is this equal to? It is equal to 1 plus I delta alpha t hat times omega times u hat dagger. What is u hat dagger? So the Hermitian conjugate of this, remember t is Hermitian, so it's just 1 minus I delta alpha t hat. And if you work this out, so homework, check. You've probably seen this before in the quantum mechanics course anyway, but this comes out to be equal to omega plus I delta alpha times the commutator of t with omega. So in other words, the i.e. the change in omega, if I say under this transformation, I'm doing an infinitesimal transformation of the operator observable omega into this new description, and I say, well, the new operator is equal to the old operators plus this small part. Okay, this small part, let's write it as delta omega. It is equal to I delta alpha times the commutator of t with omega. Now, leave that there. Now here's something interesting. If the theory is invariant under this transformation, in other words, we're performing this transformation, if this is actually a symmetry, then it should be that if I apply this result, if I apply this to the Hamiltonian should not change. All right, I'm performing a symmetry operation. If it really is a symmetry of the theory, then the Hamiltonian in the new description should be the same. So the change in the Hamiltonian should be 0. So if I now look at this general result, this we've worked out for any observable omega. If the change in the Hamiltonian is 0, then this requires that the commutator of t with the Hamiltonian is 0. All right, if our theory is going to be invariant, the commutator of t with the Hamiltonian is 0, which implies, we've just seen before we said that if something commutes with the Hamiltonian, then it's conserved. Implies that t hat is conserved. So here you see there is a very nice and deep relationship. I'm just going to write down this one last thing and let you go, is that when we write u hat is equal to e to the I alpha t hat, this thing is called this t hat, this Hermitian operator introduced, is called the generator of the symmetry. The generator of the symmetry, and these are conserved. Generators are conserved. another way to put it is to say that conserved quantities generate symmetries. E.g., the example I mentioned before for the momentum generates symmetry under a spatial displacement. D, if the theory is symmetric under a spatial displacement, the generator is actually the momentum operator, which is conserved. Okay? And in fact, you already know that conservation of momentum is related to translational symmetry. So there's this interesting thing in quantum mechanics. Conserved quantities actually generate the corresponding symmetries in this sense that the unitary operator describing the symmetry is e to the I times a parameter times this Hermitian operator, which is called the generator. So are there any questions about that? So we'll look at examples next time. We're going to look at the momentum, the energy, the charge operator, all these things, and look in a bit more detail on the symmetries, how to generate them, and there you go. So please do the homework, and if you have any questions, any problems, please email me for an office hour. And remember, the homework problems I set are chosen to reflect the kind of problems that you'll have in the exam. Okay, so imagine yourself in a few weeks sitting in an exam trying to do problems that are a bit like those homework. If you can't do the homework, you're in big trouble. So please see me. I don't want anyone coming crying to me afterward. I failed the exam, why did I fail? There you go. Please see me in the office hour if you have any problems. All right, thank you.